So my screen is visible, right? I hope it is visible.
Yes, ma'am.
Yeah, okay. All right. So let's start looking at what we have today. Right. So, so in particularly in the last week, we learned something about feature matching. We saw how to find features using SIFT, basically image descriptors that describe different key points. But now, then, once the key points are generated, once you have descriptors, what do you basically do? What is feature matching? Basically, feature matching is where uh, you extract features in each image independently, as is written here. So you have suppose two images which are looking at the same image but in a different way. Okay. Yeah. So now what we want to find out is features from this image that are basically independent of. I mean, what I'm trying to say is, suppose I'm trying to find feature of this particular peak here. Yeah. So suppose I'm trying to find the feature of this particular peak here. So all we want is that feature representation should not change if the image changes like this. So the peak here is actually translated to a peak here, somewhere here. So the feature describe the representation describing this should not be different from the one that is describing this. That is all we want to do here. Right. So what we want to do here is we want to extract features in each image independently. So suppose given this image, we extract the key points and features from here, from this image first, and then in the as a second step we take this image as input, and then we find features here also using SIFT or any other feature extractor, which will give you some interesting points, some key points, and a description for each of them. So now, what is the second step? Second step is that we need to match. So suppose, as I said, that for humans it's very simple. You can understand like uh, how this image maps to this image basically. So this particular peak that is there, that peak is actually given over here. This one is given over here. So it's very easy for the humans to understand, but obviously we have seen in the this week's class how to match. How to match these features across the images. So what you have to do is this particular feature should map to this particular feature in the second image. This particular feature in the first image should map to this particular image in the second image. This particular feature in the second image, and so on. So yes, so where were we? Yeah. So what this type of thing helps us in is, first of all, it gives us a good, you know, uh, image invariant feature. So that means what? Again, as I said, that you want your feature to not change. If even if the angle of the image changes, suppose it is rotated, it's translated, anything, we do not want the features to change even then. So that is what is what we want to achieve through feature matching. And one application is, obviously we have talked about it last week also. So image stitching, image retrieval. So these are some of the applications where, once we are able to find out like what are the interesting key points in the image, and once we are able to match them across images, then we can stitch images together. We can get so that is kind of how we get panorama images, for example. So this is one application of feature matching. So it says here descriptors for matching features between. So yeah. So what we want to do, what is happening here is that the image is basically of the same object or the same concept or entity. Just that there are two views of it, and we want to match features there so that our features are independent of the position of that object, so that they are more robust in nature. But now let's do this once. Yeah. So can anyone point out to me like one limitation with this method? So we could have stayed here only, we could have done this only, and we would have been done. So why, all these later works have come up, so much research on feature representation and all. What is the problem? What is the limitation with this sort of a, this sort of a setting? Can anybody unmute and point out? Okay, so basically, see, the thing is that here you have the same mountain, right? So you have just two different viewpoints of the, two different viewpoints of the same mountain, and you are trying to match features there in order to generate robust features. What if I gave you, suppose here in this particular image, I gave you Mount Everest, and in this particular image, I gave you something else like, suppose what? Suppose the Andes or anything from Europe maybe. So then, how do you extract features from these images? How do you know that, okay, Everest and Mount Andes do have something in common? It's the mountain factor that is the common element between them. So that is not done here. Here, in this method, you need the same mountain to be there. If it's a cycle, you need it to be the same cycle in order to match the features. But what we now want to do is we want to get some generic features out of the different objects in the images. So, it can be any mountain, but I want one representation for the entire mountain class, or whatever mountains are there in the world, we want one representation for them. Similarly, whatever cycles are there in the world, we want one representation for them. So, yeah, right. So, looking at this image, this is what I'm trying to talk about. Like, suppose you take this particular car. Where will feature matching match? Where will feature matching work? If we have, suppose, different photographs of this particular car only, then we know that feature matching works. But suppose this is one car, this is one car image, this is another car image, this is another car image. How to tell the machine that, these three images, they represent the same thing basically, maybe different features, maybe different colors and all, but they actually represent this car identity. So how to tell the model that? So their feature matching won't work. Yeah. So this is a situation where feature matching won't work. What we want here essentially is that we want to generate some representation. We want to tell the machines in some sense that, okay, this car and this car, they represent the same thing in a generalized fashion. So now so as it says here that, okay, we were focusing too much on the geometry here. Whatever geometry was here, we were focusing a lot on, the mountains, the way they are located, whether they are translated or rotated, anything. Let's not do that at this point. Let's first try to generalize our representation so that they can identify all different forms of the same thing. So if we give, for example, suppose this is Mount Everest and this is Mount Kanchenjunga, then uh, we want something so that our model, our algorithm, whatever it is, it's able to identify both of them to be the same thing. Both of them are mountains. So that is achieved through something like this algorithm, which is called bag of words. And bag of words is actually something that is very commonly, that used to be very commonly used in the language, by the language people, natural language processing people. So it's actually very simple. Yeah, it's actually very simple. What happens here is, suppose you have been given, two sentences like this. One is John likes to watch movies, Mary likes them too, and Mary also likes to watch football games. Suppose these are two document files. One this and this first one is one document, the second one is another document. Now, what bag of words does is it basically collects the words that are there in each of these documents. So it first collects all the samples that are there with you and then converts them into discrete word tokens. So all of these words, whatever you are seeing here, the NLP people call it tokens. So all the tokens are collected. So here we separately. So John, likes, to, so on. So you collect all the tokens or words that are present here in the first one, and then you also collect all that is there in the second one. Now, what you do is you basically create a dictionary of these uh, whatever words are there. So you pick out the unique words whatever are here. So suppose John likes to watch movies. Mary, we already have likes, so we won't take that. Movies is already there. Two, then similarly, so we collect all the unique words that are there comprising of these two sentences, two documents basically, and we form something called vocabulary. Vocabulary is like, whatever, suppose whatever Oxford dictionary we used to carry in our childhood. So vocabulary is just like that. It's a dictionary of words. It's a set of words. Uh, that comprises our entire corpus. Corpus means, collection of all the documents that we have, all the samples that we have, whatever, that entire thing is called a corpus. So now, what you do now, once you have formed this particular vocabulary, the next part, uh, the last part is actually pretty simple. You take this first document and you find out what are the unique words here. So John likes to watch movies, Mary too. So you collect all of them. Yeah, so you collect all of them and all you need to do is find the frequency of each. So John, here see, John has appeared one time. Likes has appeared actually two times, once here. So it will be two and so on. So you basically, from your vocabulary, you are just finding out how many times each of the words have occurred in the first document. So this becomes a histogram for your first document, and then you collect this particular document and similarly convert it into a histogram here. So these two become the histograms of for the two documents. And now this histogram, let's see, no, okay. So if you take this histogram into consideration, so what are the values here? 1, 2, 1, 1, 2, 1, 1. So these collection of numbers, they you can treat them as vectors basically. Similarly here there are all ones. So these collection, whatever frequencies you have collected, you can convert them into vectors. So taking all of these into consideration one by one, and that vector basically becomes your representation for the entire document. So here actually they have shown only the words that are there in this particular document, but actually you what you do is you take every word that is there in the vocabulary, entire vocabulary, which means that all the words that are present in all the documents, and then you basically count the frequencies. So there'll be a lot of zeros as well. So suppose football is not there in the first document, so there will be a place for football also here. So there the frequency will be 0. So in effect what you do is for document 1, you have on the x-axis you will have all the words that are there in your vocabulary, and on the y-axis you will have the frequency of each of them. And now whatever numbers you get, you collect them together and that becomes your vector that represents this particular document. And similarly you have another vector for this particular document. And now suppose if you, so now what you have is a vectorized representation of both the documents. And suppose if you want to do some sort of, suppose matching, some document matching, so then what you can do is you can find the cosine similarity between these two, document 1's vector and document 2's vector, and that will tell you suppose how similar are these two documents. And uh, uh, there are tons of other applications to this bag of words methods. I'm not going to go into them at this point, but let's, okay, yeah, so let's move to, so this was the language part in very short. So let's see what happens in the image part. So suppose now images, it this all of this is very neat when it came to languages. So it's not very easy when it comes to images because images do not have words like this. So this is very comfortable. Comfortably, you can extract all the words and their frequencies and all. But what to do with images? Now, what we understand, different people apply different techniques for each of for converting images to bag of words. But what they generally, what one common approach that they take is, suppose you have an image like this, you'll basically divide this image into patches. So you can see some patch here got the eye, some patch here got the mouth, there's the nose, and so on. So you'll convert this image into patches, and then whatever patches look very similar to you, you'll group them. So suppose you have this particular image. When you divided that into patches, you found that this is the basically the middle of the eyes, then the nose, mouth, this left or right eye. These are all very very similar regions in the image. So you take them and you group them together, and this group will comprise of one word. Similarly, you take this cycle, you divide it into patches again. So maybe one tire comes up in one patch, this particular thing comes up, the seat comes up and all, and you find that okay, in the entire image, suppose there are other things also in the entire image, but you find that okay, these different parts of the cycle basically try to represent one thing, or they are very similar in nature. So then what you'll do is you'll group them into one visual word. Similarly, the same thing with the violin. So basically what you are trying to do is you are trying to patch up the divide the image into different patches, and then you are trying to in some sense detect what the entire, I mean, what are the similar parts in the image that can constitute an object. So now what has happened is, from these three images what we got is one of them gave us visual word for a face, some other gave us a visual word for a cycle, and some other gave us a visual word for a violin. So now what you'll do in the image, for example, is that uh, take your test image, whatever image you have, and now you'll do a similar thing as this one. Now you have formed the visual words. What all you have to do is, based on the visual words, you'll arrange them on the x-axis like this, and you'll count how many times the visual word has appeared. So for example, if you take face as a visual word, and suppose there's an image with 10 faces, then the face visual word on the histogram, there'll be 10 counts for the face visual word, face based visual word. Similarly, so here you can see that the regions representing the face, they are they have a large value in the histogram, whereas others have negligible values. Similarly, in the second image, you have a, suppose this one looks like a cycle. So the cycle based part has the most frequency, so it has the highest value basically. So this is how you are converting. So just what all you have to do is translate this problem to this. So this is how you find the visual words in the image, and this is how you translate them to the histograms. And as I said, your uh, the the vector representing, so what you are trying to do is you are trying to represent the image using a vector, and the vector representing this particular image will be the numbers that are given here. So this is, suppose this is something 1, suppose this is 10, suppose 1 again, 9, suppose. So this, the number that you got from here will be the vector that is representing this particular image, and so on. So now what you get is, in this form you are getting a um, what do you call, a vector representation for the entire image, for groups of images. So now a little bit more details about how this happens. So suppose you have 5 images in your database, so you'll already have a database prepared for all these images, so that you can store the visual words that are present in them. So suppose you have 5 such images which you have already processed, and you have these 6 visual words in total in your vocabulary. So just treat it as if now, after this step, everything becomes like the language part, the sentence part. So So this means this particular vector means what? That this column basically represents your image one. So there are six visual words there. This means that visual word one is present in image one, but visual word 2 and 3 are not there. Again, visual words 4, 5 and 6 are there. So that is how you interpret this particular matrix of which we call the image database. So now suppose you want to retrieve images. Okay, so you have been given a new image and you have again converted that new image into bag of words as I described. Now what you want to do is, given this query image, you want to find out what are the most similar images. What is the most similar image, for example, um, in this database, most similar to the given query image. Okay, so all you have, what you can do here is that you can so one of the most easiest things that one can always think of is that you have a vector here, and these are also vectors of the images stored in the database. Then why not do, as I said in the one of the previous slides, so here I talked about cosine similarity, dot product is there. So why don't you compute the dot product between this query vector and all the vectors that are there in the image database. So you do that one by one, and then the I mean, it's intuitive and easy to understand that whichever images give maximum score in after your dot product, that those images are the ones that are the most similar. So, for example, here if you take this vector and do a dot product with each of these, you get you get this new vector, which is a similarity vector. So, what this means is, with the query vector, this first, these are the five images that we had taken into consideration from our image database. So the first image had a similarity of 2, second image had a similarity of 1, and so on. Which means that this particular image, the first image, had the highest similarity with the query image. So that is one application of bag of words where you extract, you can retrieve or you can find similarity with other images using this. So in other words, here whatever I was saying, suppose I have a Mount Everest image and Mount, suppose something else, Kanchenjunga image, then this is one way to find similarity between these two images. So suppose here this is the Mount Everest image and this is the Mount Kanchenjunga image. This one suppose is a Mona Lisa portrait, this one is something else, totally something else, and so on. So because here also there's a mountain, here also there's a mountain, you'll find a bigger similarity score here. But now there's a catch here. There's a little bit problem in the algorithm is fine, but it's not very efficient. So what is the problem? The problem is that suppose again it's much more simpler when you look at it from the language point of view. So you have been given, suppose these, here there are two documents, but suppose there are, in total there are 10,000 documents. Okay, so there will be so many words. So suppose there are 1 million words that you have gathered out of those 10,000 documents. Okay, but now see here, in your first sentence, first document, you have only what, 1 2 3 4 5 6 7 8 9, 9 words. So out of those 10,000 you only have 9 words present, and that too they are not unique, right? So sorry, I had said I think 1 million words. So out, out of the 1 million words, only these 9 words are present. Which means what? That if you kind of try to find out histograms of this form, they'll be very sparse, because inside one image or one sentence, you'll have very less number of words compared to your entire vocabulary. So imagine the world, there are so many objects, so each object will have so many representations. There are so many animals, faces, trees, whatever, whatnot. So if you want to, this kind of a vector, if you want to represent your image through this kind of a vector, it's going to be very sparse, because your image will contain maybe only 2 3 objects, whereas in the world there are suppose thousands of images. So all of them will be very sparse. So it's kind of inefficient where you go on calculating the dot product between each of them. So 1 into 1 here plus 0 into 0 here, 0 into 0 here, and so on. So it's quite inefficient and it will take a lot of time, and the cost is, I mean, for nothing. Basically, this is a very, very sparse vector. So why are we doing all this? I mean, why are we putting so much effort into this? So instead, so that's what it says here, that these are very smart, sparse matrices and vectors. Okay, and that is why we'll do something in an inverted sense. So what we'll do here is basically, instead of um, you know what we are doing here is we are going at each dimension. So basically we are going at each visual word in the in the image, and then we are trying to find out like how many you know how many of them are there in the database image, right? So instead of that, what we are saying now is that we'll take each word, which each visual word. So suppose this is your query, and query image. So the query image has suppose three, I mean, it's a so it has only three objects, three visual words. Suppose one is this green one, then blue one, then red one. So these 54, 67, 72, these are just numbers on your dictionary. These can be anything. So as I said, here you are forming a vocabulary. Suppose vocabulary is similar to the Oxford dictionary that you carry. So suppose these are the 54th, 67th, and 72nd words of your dictionary. So these are the only three words that are present in your query vector. Now what you can do is, instead of going word by word and doing a dot product and all you have to do is, suppose these okay, let's go here. This will be a little bit better. Okay, here. So this one is visible, right?
Yes, ma'am.
Okay, let's switch on to video mode. Yeah. So now, suppose you have some database images like this. So from this particular row to this particular row, and suppose they have been given some indexes, some numbers from 12 to 22. These don't matter. So now what you'll do is, you'll take this first word and you'll try to find it in each of these images. So is it there in the 12th word? No. 13th? No. Sorry, 12th image. These are all images. So is this word present in the 12th image? No. 13th? No. 14th? No. 15th? Yes. So okay. So it's like this. Sorry. So yeah. So then what you do is, because it was present in the 15th image, you just put one here. Similarly, now again you go for 16, 17, 18, none of them have this particular visual word. So again you find it in 19, that is why you put a 1 here. Similarly, in 20 it's not there, in 21 again it's there, you put a 1 here. Okay. So now, so this says what? That after checking the first word, you have only in your image database, three of them are having this particular first word. Now let us go to the second word. The second word, what we are seeing, that it's present in 13, image 15, and image 19. So similarly, what you do is, in place of 13, previously there was nothing in it. So now, since we have found the first for the first time this blue word has occurred, so you put a 1 here. Now coming to image number 15, already the green one was found here. So now you have found another blue. So now this here 15 was 1 here already. So you make it 2. Similarly, when you go to this 19, you already saw that the green one was here. So now you have to add the information of the blue one. So here the number count becomes 2. And now I think it's understandable to you that you take the third word and do the same exercise. So third word actually is present in this 15, 17, and 22. So for 15 you change the 2 to 3 and so on. The others will get a score of 1 because previously there was nothing for them. So now at the end of this particular exercise, what you get is, you have got an image wise score, which is this is what you wanted. So this is basically the indirect way of calculating the frequency only. So here you see that 15 has a frequency of 3, 19 has a frequency of 2, and so on. So basically you get, so what, so no, so sorry, so sorry, this was not the this is not the frequency, this is basically the similarity. So my bad. So yeah, so what you get here is you have these images from 12 to 22, and now you saw that 15 has a similarity score of 3, 19 has a similarity score of 2, and so on. So directly from here you know that 15 is the most similar image to your query image, whereas 19 is perhaps the second most similar image, and so on. So the others are maybe less similar or not similar at all. So this particular inverted file index algorithm, whatever it's there, it's actually giving you directly how similar your query image is to the database of previously present images. So this is how you use BOW for image for retrieval, for finding similarities, and so on. And just a little bit of note on how this is happening. So as I more or less, I mean, whatever I've said in words, these they have just translated that in terms of maths here. So each image is represented by a vector z, uh, belonging to R of k, where k is the size of the code book. So so k here is basically the number of elements in the vector. So this is basically, k here stands for the size of the vocabulary or code book. I mean, we use these names interchangeably. So given a set of n images represented by matrix z, uh, so z is the matrix that I showed you. Okay, it's not here. Yeah, z is basically this particular vector, this particular matrix. All you have to do is, given a query vector q, all you have to do is, as I said, that one way is to do the dot product. So this dot product basically gives you, how similar this s small s basically gives you the similarity score of each query image with respect to the already present collection databases of images. So that is more or less what is BOW about. And just a small thing that yeah. So I had one question for all of you. So let's skip these parts. Yeah. So I have one question for all of you. So, like, if you look at whatever, if you understood what I said, or whatever the other my colleagues or sir said, can you point out like one one or two maybe limitations of BOW? What is wrong with this formulation basically? So good things are like we are able to now you know we can treat Mount Everest and Mount Kanchenjunga together as one particular entity, one particular concept, that is the mountain. But there is something very, very, there's a big flaw in this particular formulation. So, can anybody suggest what is going on? Okay, everybody is way too
Hello.
silent today. Yeah,
Uh, uh, I just want to try. So it can like distinguish between dog and cat, but it may be difficult while distinguish between dog and cat because they are having more similar features. So
right.
the repetitions and the functions will be there. So histogram will not be like that in that case.
Yeah, so you are saying that it cannot really distinguish between, if suppose your image has two dogs, so it
Yes.
can't. Okay, okay. Yeah, that's a valid point. But another point that I would like to, so if you look at whatever these people did, I mean, in the slides, whatever is given, one basic
Hmm.
problem with this particular method is that it's not taking into account how your dogs are placed in the image. So it's not taking into account the geometry of it. Yeah, one definite limitation is what you said, like it's, if there are two dogs, it's considering both of them to be almost same. But
Same.
yeah, so that is one drawback. Secondly, how are the dogs placed, what are the dogs doing? So nothing of that sort
Hmm.
is getting, you know, we are not taking any of them into consideration in this particular formulation. So that is why bag of words, while yeah, it's a good way of generalizing vectors, of representing, images in terms of words. Yeah, this is a good way, we agree. But yeah, that is why we have so many so many other sophisticated methods that you'll go through as and when your classes progress. And that is why deep learning came up. So how to distinguish between, suppose, two elements of the two instances of the same, entity, perhaps. So those things you'll see, but there's a very brief, I'll briefly describe, this new method called vector of locally aggregated descriptors. So this is basically, this is a very similar. Yeah.
I have one question on the back efforts
Yeah,
before.
sure.
So in NLP, it's very clear how
Hmm.
do you generate tokens, right?
Hmm.
Somewhat. So
Hmm.
so like there is a space between words, or there is some delimiter very easily creating
Correct, correct.
tokens.
Yeah, yeah.
Whereas for
Yeah, images,
vision,
it's a bit fuzzy. I agree. It's a bit
right?
fuzzy.
So
So there have to be, so here things are not as, distinct as the words, right? So you have to form heuristics so that you can convert this particular figure into, suppose, a collection of words. So I believe in class what sir said is something like this, that you divide the image into different, blocks, maybe what we in deep learning language we call it patches, basically. So suppose, so like it's given here, you have this particular area, then the nose area, then the mouth area, and so on. And there are other objects also perhaps in the image. And now what you do is, you'll, whatever patches you get in the entire image, you'll try to cluster them. Okay, so suppose there's a this woman is there, then suppose the entire thing is there, suppose this is entirely an image. So there's a woman, there's a cycle, there's a violin. So now you have divided this image into a grid. Patches means all you are doing is you are dividing the image into a grid, and then you're converting that image into, I mean, you're taking out each cell in the grid and trying to see what is there inside it. So now what you'll do is, so now that you have broken the image into grids, you'll have many small pieces like this, whatever is given here. And now what you'll try to do is, based on these, whatever patches you got from the the entire image, suppose, as I say, this is suppose one image, the entire thing is one image. So what you do is, whatever patches you get, you try to cluster them. So clustering means what, you are trying to group the similar things into one group. So then after clustering, you will find that, because these cycle parts are similar in nature, they have become one group. The violin parts are similar in feature. So if you had broken this into grids, you would have gotten some small segments of the violin. But because they are all similar in nature, they'll fall into one group. And similarly, the facial features will fall into another group. So whatever groups you get at the end of, this clustering methodology, you'll treat that as a word. So again, this is a heuristic. This is not as straightforward as dealing with words in sentences. So different people follow different approaches, but this is a very basic approach as to how you can, tokenize image, consider images as words. In fact, if you once you go into deep learning, and you go into, very sophisticated architectures like transformers and all of them treat images as, they do the same thing. Even now they divide the image into, grids and patches, as I said, and then they, uh, you know deal with the individual patches. So this patch level, dividing the image into in this patch level way is done even today. So yeah, this is how you get the visual words, basically. So
thank you, thank
yeah,
you. Yes.
okay. Correct. So now, just a very short description of what this BLAT is doing, vector of locally aggregated descriptors. So as I said that, it's already written here, kind of, that it's a this particular method BOW, it just takes the scalar frequency into consideration. Very, very limited information is there about the other things. Whereas you can, if you again when you proceed with your deep learning classes, you will see that deep learning has progressed so much because they have converted everything in a high dimensional feature space. So all the objects, whatever are there, whatever are present in the images. So this particular vlad algorithm also deals in the feature space. So it's not something scalar like frequencies, it's a continuous, it's a vector space basically. So you are converting everything into vectors. So suppose you have an image, uh, uh, and that image is represented by these hollow circles. So the circles with white in them. This is just one image. All the white circles that you are seeing, 1, 2, 3, 4, 5, 6. So all these six are basically part of one image only. And now suppose you have these visual words W1, W2 and W3. These are already there in your vocabulary. Now, what you want to do is you want to find a feature for this particular. Uh, so yeah. So you want a basically you want vectors. So what you do is um, yeah. So what you do is you have this already. You have this visual word W1, and now you have these features. These two green features that are there, so that are present in the image. Now what you do is you find the distance between this particular hollow circle and this particular visual word. Similarly, this find the distance between this particular feature and this particular visual word. And now so that distance is given by this vector. So the vector connecting these two this visual word and this feature, and this visual word and this feature. So now um, what you do is you have so these two vectors are there. All you do is sum them up. So if you sum up the vectors here, the sum will lie somewhere in the middle, somewhere maybe here, somewhere here. So that sum becomes your vector representation for first visual word W1 basically. So here what you were doing in bag of words was that you were just collecting how many W1 visual words were there in your image, and here in this example that is 2. So your answer would be 2 here. Instead of that, you are giving for given your image, you are generating a separate vector for your visual word W1. So that is given by this u1 vector, which is nothing but the sum of these two vectors. So these vectors represent the distance between this feature and this particular visual word. You take these, you take the sum, which will lie somewhere in this direction, and that is this u, that resultant vector u1 basically represents your vector for this particular image for this particular visual word W1. Similarly, you have W2. So W2 has three, suppose so there are three features in the image. So what you do is you find the distance between W2 and these three, and you add them up, and that is given by, suppose, this particular this somewhere some direction like this only. And so that particular thing is given by u2, and similarly you have this here, based on this you have u3. So now what you so this basically gives you, given an image, you have, suppose if your vocabulary has only three visual words, you have three vectors for each visual word. So that's what it says, that it yields a vector per visual word. And it's a little bit more descriptive, because you're dealing with vectors here instead of just raw frequencies. You have more, basically this is a more informative way of dealing with images. So converting everything to the vector space, this is actually a very popular way of representing images. So yeah, that's a very short description on Vlad basically. So now one thing that, yeah, so before doing the code walkthrough, a very small description again of this particular thing. Okay. Yeah. Okay. So now let's again go back to the first slide. Yeah. So here what I told about. Let's again go back. Suppose we go back to the world of feature matching once again because we need to do some code walkthrough. So what we saw here is that we want to suppose this is the top of this is the peak of the mountain. This is the peak of the mountain in the first image, and we want to find out what is the peak in the second image. So that this step is called this matching features across images. So how to do that? So if you are given suppose two images of the same object which are a little bit different, how to match the points from one image to another image. I mean points that are representing the same thing. So those things all of them can be done through I'm sure you have seen this in the class and in the previous lectures also that they can be done by some simple geometric transformation. So suppose so you have been given two images I and I hat and they are equal at points suppose x and x hat. So that is what I was talking about. So in this image suppose in this particular peak is at x and this particular peak is at x hat and this is I and this is I hat. So they are suppose equal in these two positions obviously because they both of them represent the peak of the mountain. So what does that mean? In this particular image, we can say that yeah. So this peak at this peak at point I mean some location x in image I has been mapped to this particular location x hat at image I hat. That is what it says that x is mapped to x hat. So how to find out this x hat basically? So you are given a image I and you know of a location x. So what you want to obtain is this x hat which is the new position of the same thing in the new image. That can be done linearly through linear functions where suppose this is given by capital T. So one thing that you can do here is so this particular calculation is pretty simple actually. So suppose you are given this particular triangle and what you want to so the triangle has three nodes x1 x2 and x3 and now in the next image in the second image what you get is a very similar triangle just that this entire thing has been shifted by a little bit to the right. So now but because it has been shifted to the right, your what you have to do is what has happened is your points have changed. So x1 has changed to x1 hat, x3 has changed to x3 hat, and x2 has changed to x2 hat. So your coordinates are basically changing because of this. So what happens is that so maybe you can go through these things in on your own time in more details, but you you can directly if so given a point like this in the original image xy you can directly go to x hat and y hat in the transformed image in the other second image basically through some matrix transformations through some linear transformations basically. So given this particular matrix once this matrix operates on your coordinates you'll easily get the coordinates in the other image and that is how you are supposed to match the features at this particular location. Right. So similarly, there are other other various transformations that you can do like rotation and all. So now, for every one of them, you'll see that there's a you have an original coordinate, a final coordinate, and a matrix that is converting this original coordinate to the final one. So why not instead of so all you have to do is just convert this system like this into a linear system ax equal to b and just solve this one. So what is x? X is basically the actual original coordinates. B contains the coordinates of the image in I hat and a is basically the model parameter. So whatever you want to do, I mean, whatever operation you want to do, that is given by this A matrix. So um, what we can do is we can solve this system using least squares. So again, if you don't know least squares, please go back and look at it. So what do we want to do here is, given a suppose so given these points like this, what you want to do is fit a line. So that is how, I mean, that is what least squares is about. So you want to fit a line given a set of points, data points. And given, suppose in this particular image, what you see is that it's all very cleanly situated, so you can put your line very comfortably here on top of these points. So as it says here, it's clean data, there's no outliers, and you have a good least squares fit. So basically you have been able to fit it with a good line. So now what happens here is that you have a in this is a second situation where you have some points and a lone point here, which is a bad point basically. So what it says is that this is a gross outlier. Okay, so now if you try to do least squares here, what will happen is this particular this setting is gone, where you have a good, upward trend here and you can fit a good line here. Because of this outlier, your line will now come out to be bad. Okay, so that is why it says that least squares fails here. So this is a very common problem in machine learning and linear regression, where you have a uh, you know um, a bad outlier point, and it's a very, I mean, it's a matter of lot of research as to how you can deal with these. So now there's a this algorithm called ransack. So I'll very quickly go through it. So this algorithm acts on top of least squares method to deal with data with outliers. So let's yeah so the what they're trying to do is very easy. Suppose you have a two dimensional data, and what you do to find, I mean, in this algorithm is that to identify outliers, you just first, as a first step, you pick out 2 points at random from all the points that are there in the image, and you draw a line through them like this. Now on top of this line, what you'll try to do is you'll try to set a margin around this particular line, and what you'll count is how many data points are there within this margin. The idea being that if there are many data points, then this is a good, these 2 points are good, because what we want is just that whatever line we draw, we want most of the data points to be very close to them. So you count the number of data points that are there within this margin, and called, basically they are called the inlier points. Why? Because they are lying inside the margin, right? So now you keep on doing this, you keep on finding points at 2 points at random, and you keep on doing this until you get a good, basically good fit. So as is shown here, it's trying to pick up many such pairs of points, and it's trying to count the number of uh, inliers that are there within the margin. So after doing this, so this particular line, once they chose, they saw that, okay, fine. So within the margin, there are so many points, which means that this is a very good fit. And what you need to do is, since this is a very good fit, it's the best hypothesis so far, and we should store it. So again, the next fit is not very good. So here the number of points inside the margin is pretty less. So we won't store it. We won't store this one, and so on. So let's go through the code very quickly once. Okay, where was it? Yeah. Hmm. So this is the setting for ransack. So what you want to do is, you have been given a linear system of this form, where y equal to capital X beta plus epsilon. So what is capital X is a matrix. Beta is a parameter vector. Epsilon is a noise vector. So you do an x beta plus epsilon and you get your response vector, which is given by this y. So again, I mean, like, so given a form, I mean, given an equation of this form, you can convert it to the matrix form using, I mean, the system of linear equations like this, and you want to solve it. And if you go through linear regression, you'll see that, so you want to solve for beta basically, you'll see that beta turns out to be something like this. So if you directly solve the problem in this way. So now what the code here wants to do is that they want to use ransack and they want to avoid outliers in one curve fitting. Therefore, they'll basically they'll calculate multiple betas uh, using this formula, and they'll try to find out the best one, which doesn't have much outliers. So yeah, so they have so there are a couple of import functions here which will use these mean squared error, sample without replacement, and so on. And this class regression is what they are using to solve this problem of finding the good betas. Yeah. So order is basically so here you are trying to fit a polynomial of a specific order. So here, as they say, that this for a given polynomial of suppose order m, and you are trying to fit a polynomial of order m here, and that is given by this. So beta is already there, and beta is a vector of zeros, and so iterations is basically some how many times you want to do this. So whatever algorithm I just told you, how many times you want to do this, and so on. And so let's look at the solve function. You can go through, because of lack of time I'm having to go very fast, but you can go through the code at a pace that you would like. So yeah, so this is the solve function. Solve function actually is the one that is solving this using ransack. So it's everything is given here in the as parameter. So it's a function to solve regression using ransack. So these are some initializations basically. So close points is probably the number of points that are you are close points is basically the number of points that are inside the margin, and you are initializing it to be 1. And similarly, these are all initializations of the same thing. Okay, so what you do is, so you have a max number of iterations for which you want to do this, and what you do is every time you want to sample without replacement 2 points, suppose, okay, from your data. So you sample 2 points from your data every time. So here I'm considering 2. You can generalize it as you want, right? So now what you want to do is you have the two x's, and now you do a polynomial fit on top of that to get your beta. So basically you are, yeah, so you have the x's, you have the y's. All you want to do is you want to find out what are the good betas for them, right? And then once the coefficients are already there, what you do is you predict the you I mean your, now your coefficients are there, so you can fit the model. So you do a self dot predict of x, and now also you have the true y values and the predicted y values. So you do some sort of error measurement, either through L2 either through sum of square error, or through this absolute error or anything. So you find the error in this way, and then this is the algorithm that we talked about. So basically uh, what yeah, so basically what they're trying to do here is, once you have suppose picked up those 2 points, as I said, as is given here, where were we, yeah, this one. Yeah, so now that you have gathered these 2 points, what you want to do is fit a line for it. So that is where you are predicting the betas, where you are finding the beta coefficients. And now what you want to do is you want to find out how many points are there which are inside the margin. You set the margin and you are trying to, so this threshold is actually, this threshold basically stands for the margin, and you want to find out how many points in your data set are there inside the margin. So that is given by this particular block of code where so you want to find coordinates of points having error less than threshold. So you want to, so this threshold is the margin. So whatever points are there whose error value is lesser than the threshold, you pick them up, right? And so this particular block of code basically finds the, so here you basically find those points, the inlier points. So this is simple NumPy coding. Again, just go through it on your own time, you'll understand it. It's not very difficult.
Uh, Ma'am, may I ask a question?
Yeah, sure.
It may be sound silly, but like I don't know like where to find this notebook. If you can just guide me.
Oh, yeah, sure. Okay, so just a second. I'll just share this one. Okay, no, didn't I copy it? Oh, okay. Yeah, you
Thank you
have.
so much, ma'am.
Yeah, sure. So yeah, now what all that is, so now you have found the found the inlier points with respect to the line that you found, right? And now all you have to do now is find out base whether the line that you have found at this point is better than the previous lines or not. So that is what is given by this block of code. So suppose you have what it's trying to do here is it's trying to find out the mean square error between the new model and the old model. So old model means suppose you are doing it for some iterations, and now based on the new line you calculate the error that your model has. And if now your error is but suppose minimal, lesser than the previous model's error, then you basically store this particular model. So that this part of the code is basically what is shown here. So let's start here. So here you found something, you found certain lines. So this is, suppose there are 5 points uh, uh, inside the margin with a certain error, and now you find there are suppose 20 points inside the margin with lesser error. So basically this line is better than the previous fit, so you store this. Similarly, you suppose you find here that there are 30 points, and you know, but this is not a probably the overall error is perhaps more. Then you discard this line again and again and again. So remember this, but we had chosen this particular line to be the best one. So we discard, and now suddenly we come across a line where we can see that there are so many, suppose 100 points there in the inside the margin, and the error also is pretty less, is the least at this point compared to the previous lines. And so now you store this one as your best fit, and again this one is worse, so you don't store it, and so on. And this is how you get basically this one to be your final line. So that is what is shown here. So yeah, we are out of time today, so just go through it, go through the code, I'm sure. And yeah, this is, once you plot everything, this is how it looks like. So you can see that these are all the data points. So here, it's a little bit confusing because they have already mentioned what are the outliers and inliers and so on. So you can see that while you have a trend like this in the data, these points are really misleading. They these points, then the bottom points, this point, so they really mislead your linear regression algorithm. So that is why this ransack algorithm is successfully able to deal with these outliers. So previously, before running the algorithm, nobody has told you that these are the outliers and these are the inliers. This is what the algorithm finds. So the curve that it has found through this, the curve found by the ransack algorithm is this one, and you can see that it has so many points lying across, on both sides of the curve at a smaller distance. So it's able to handle the outliers well. So yeah, I know I went through it a little bit hastily. So I'm sure in the previous classes it has been explained in a much better way. So just go through the code and try to play around with it a little bit. So it will be much more clearer then. Fine. So we end the call today, and we'll meet next week.
Thank you.
Thanks.